All right, this is about where we left off last time. We finished that point 3D class, right? Looks something like this. It's a fairly simple class, which is often actually very nice. We like to have, this is effectively just like a class full of data. It's a class that's a collection of data, and it's got some methods that are nice with it. For example, okay, we've got this distance from other point. Okay, that's great. Sure, we could do that. And we have an EQ and a repr. Very simple, and there's nothing wrong with that. Classes are not supposed to be these big complicated things. I mean, I guess they can be, that's fine, but that's not what we're going for here. That's not the idea. And I don't mean that that's not the idea in 161. I mean, that's just not the idea with programming in general. Now, the purpose of this class was to build on the sphere, well, not really build on, but like to modify the sphere class we did before. So what we're going to do is where the sphere class previously had an x, y, z and a radius, we're going to modify it such that it has a point 3D and a radius. But the point 3D has the x, y, z. And part of the reason for this is to show you the differences, but another part is that it shows how we can like offload some of the responsibility of one class to another class. Okay. Oop, don't need that anymore. So the sphere class. Now that we have that, we can modify our sphere class to look something more like this. No, not that. Copy. There. I'll just get rid of the doc strings to simplify it. There. So now, this is obviously not the full class. We're going to fill it in as we go. But we have the class, we're saying it exists, and we've got our initializer, the constructor. But here you'll see it takes a center point, which is a point 3D, and a radius. And this class will have an attribute center point and a radius. There we go. Great. So nothing too crazy at this stage. We get rid of this. If we go down, okay. From looking at the above code, we could see that removed x, y, z, but we still have it indirectly through the point 3D object. And then we got to add a couple of methods. Now, these methods here, these were like the basic sphere ones, basic geometry, of the sphere. And you'll see that none of these actually depend on the point 3D. The diameter doesn't matter. Surface area doesn't matter. Volume doesn't matter. All it cares about is the radius. It doesn't have anything to do with the point 3D object. So those are going to stay the same. It's entirely fine, nothing crazy. But if we were to go look at the distance between centers, this method before would calculate the Euclidean distance, right? It would take the circles x and the other circles x, then the y's and then the z's, do their differences, square them, sum them up, square root, whatever, get the Euclidean distance, great. But here, we're not. I mean, we are, but we're doing it via the self's center point's distance from point other's center point. Do you see how that's working now? So this logic is offloaded to the point 3D objects class. We ask the instance, hey, my center point, how far are you away from their center point? I realize if you open up that code, it's the same code, but the point is not what all of the code says together. It's kind of like where the code is and what code has what responsibility. It's part of the design of our software, which is an important consideration. But do you see how now I ask my center point, how far away is it from the other ones? Because my attribute center point is a reference to an object that has the method distance from point. You see? Yeah. And you can also see this is far more general, right? A point, center, distance from point. That's a point asking how far away it is from any other point. It has nothing to do with the center. Like, the point 3D class doesn't care if the point represents the center of a sphere or just maybe it's a corner of a cube, or maybe it's just some point in three-dimensional space. I want to know how far away from the origin. Whatever. It doesn't matter. Where before, it was really tied to the fact that it was the center point of a sphere. Where now, that's just a consequence of the sphere class. The point 3D class doesn't care what it is. It's just a point. You see? Yeah, it's important to understand. And then with that, well, these are actually, we don't even need the, like here, this one. Oops. There. Distance between edges, well, this just calls my distance between centers and removes the radii. Overlaps, same idea. There. These two methods are actually the same. The only method that really changed so far was this one. That's it, right? That's it. Everything else is the same. The constructor's different. Okay, yeah. The EQ is going to be different as well, which we'll write. And the point 3D will be a little bit different as well, but that's basically it. Any questions about what we see? Now's the time to ask. Now, how do we define equality? Well, this one's kind of interesting, but it shouldn't be mind-blowing. But when you look at this, okay, is the other thing an instance of a sphere? Okay, if it is, okay, so far so good. If their radii are the same, or if their radius attributes are the same, whatever. But over here, you'll notice I'm also comparing the center points. I'm not comparing an x, y, z. I'm comparing a center point. Now, we all know that the center point contains an x, y, z because we wrote it. But as far as the sphere class is concerned, it doesn't care what's inside of here. It doesn't care what is a center point. All it cares is, well, are they equal? Do you see what I mean? I don't care if they're equal if it's a Tuesday afternoon. I don't care if they're equal because whatever reason. All I care about is knowing whether or not they're equal. Because if they are equal and the radii are equal, then the spheres are equal. That's what's important. So we like hide, in a way, what it means for them to be equal. We just need to know, are they equal? But what must be the case when, like, look, I'm saying, does this center point equal that other center point? This requires that there exists an EQ or a underscore underscore EQ underscore underscore in the point 3D class, right? So if you ever ask, now, by the way, like we talked about previously, if we don't write the EQ method, you get one for free. You don't see it, but it's the is relationship, basically. But here, if I ever wanted to know if two spheres are equal, I could write here. Let's put that in. Great. Okay. We'll go down here. And then that requires a point 3D. 0, 0, 0, 5. And then I'll just modify it. And then print. Oh, what did I, oh. What am I doing wrong now? Open, close, too many? There, perfect. Now you like, wait, what's going on? I could have created these beforehand and stored them in a variable and then put them in here, or I just created them in the line just for simplicity. So don't get too weirded out by that. I'm creating the object in line and I'm immediately passing it to the sphere's attribute by calling the constructor, that's all. But When I ask this right here, this goes and calls this method. But then this method goes to the point 3Ds and calls this method. Do you see? Because this is, well, how point 3Ds are defined to be equal. So we use the point 3Ds equal. Effectively, so then I could ask the question, well, how does Python know which EQ method to run? I wrote two here, the one in the sphere class and the one in the point 3D. And the way it knows is, well, which object did you ask? If I asked a sphere, if it's equal to something, I'm going to use the sphere's equals. If I ask the point 3D, it asks the point 3D class's equals. What's going on? Clear or no? I've seen a lot of blank faces, so I don't know what that means. Your faces have not gotten any less blank. Now they, yes?
For the second line, or like the sphere A equals whatever.
Yeah, down here, yeah.
Do you have to run both the one above and then also the earlier one from lesson 20 of class sphere?
Yes, because if I don't, Python will be like, what the hell's a point 3D? Yeah. But so yes, you would have to do that. Yeah. This is a funny consequence of like Colab by this like notebook style programming where we've got these like individual cells. But like if this was like next semester, for example, and you're writing code, like this is less of a problem next semester, how we would be doing things. But good observation. So the point is, we are like cascading. If I ask a sphere if they're equal, it requires that we know what it means for point 3Ds to be equal as well. Because otherwise I wouldn't know how to compare their center points, which are point 3Ds, or references to point 3Ds. You see? Pretty neat. Other questions? All right. Then, in a similar way, check this out. I'm going to add the repr for the sphere. Now, take a moment and look at this code. All right? I say sphere, center point, and then like, oh, well, what's the center point? But the center point, like, okay, let's go, just skip this for a second. Let's go to here. Give me the radius value. Well, that's just like an integer, right? Is it 7? Is it 70? Whatever. I don't know. Doesn't matter, whatever. But this is an object, right? So how the hell do we represent an object? By defining the repr for that object. This class says this is how you represent a point 3D. So down in the sphere class, when I say, well, okay, give me the center point of point 3D, it's going to be the string representation of the center point object that we have. This is probably best demonstrated with an example. So if I say, just print out do you see? What do we see here? Well, we see, oh, well, this is a sphere, where the center point is equal to, oh, a point 3D, x, y, z. Radius. Do you see? And if the point 3D had an object, which had an object, which had an object, if you did it like the right way, it would be all the way down, which is pretty neat. Now, part of the value of being able to do this is, like, in certain programming languages, like older ones, like let's say like C++, for example, like you couldn't do something this way, where like, let me try to make this more clear. Like this here requires that there exists a method that tells Python, how do I get a string representation of that object? Okay? It requires that it exists. If it didn't exist, this would crash, right? Because, well, how else would it know how to convert it? But remember how I kept saying, if you don't write the repr, you get one for free. Meaning Python can guarantee that there is a repr. It does exist. It could be a terrible one, But because it exists, I know it's safe to run this line of code. It won't just crash randomly as a consequence of the repr not being defined. Let me go back here to make sure this demonstrates the point. I'm going to get rid of this repr. I'm going to rerun the code so it's gone. If I go here and I rerun it, this should be, pardon me, this should be what you expected to see. Because now we just fell back to the default string representation of, well, what's the point? Well, it's a point 3D object that blah, blah, blah. You see? By the way, if you didn't notice, every time you hit run, you're like, why is that number? It's the same. Why is it still hit? Because every time it just throws it in somewhere else in RAM, right? Yeah. Yeah. Yeah, right? Yeah. Yes?
So just to make sure I'm understanding this correctly, the repr we just added references the other one?
So the repr in the sphere, because by virtue of like being like, well, give me the string, this will automatically get the string representation, the f string. This would be like writing this. It just does it automatically. Okay? Give me the string representation of the center point. Oh, how do I represent this as a string? And it goes and runs the repr defined in the point 3D class. Does that answer your question? Now, we got rid of it, right? So we didn't write one, so it defaulted to the old, not that helpful one. But the point is, it existed. So it's safe to run. If it didn't exist, we would get something like, could not find method repr, right? But oh no, repr exists, it's just the default one. Similarly with equality too, with equals, how you define equals. This becomes, so one of the like nice things about Python, one of the reasons I like Python for intro programming, there are some reasons I don't like it. Every programming language just has pros and cons. But the reason I like Python for like 161 is it hides some nuance that's not overly important for the things that we're trying to learn. It's not to say that that nuance is not important. In fact, that nuance is exceptionally important. But it tends to, for me, I feel like it tends to get in the way of the core things I want you to learn. When we shift to Java next semester, Java, if you're thinking, man, Java, that's going to be, no, it's not. There's always there's a little bit of like a learning curve, but you'll be fine. Don't worry, you'll be fine. Because like all the algorithms are the same. What you're going to get tripped up on is the syntax, but don't worry. You just go to Google and be like, how do I do a for loop in Java? Oh yeah, that's how, right? That's how you do it, okay? But the point is that I'm going to make is Java actually will make some of that nuance more explicitly clear by how you must write your code. Java forces you to be more explicit and like very intentional with what you're doing, which is a very good thing. Java, by the nature of like the syntax, will force your code to be more correct than Python does. But that's all to say like, oh, look forward to Java next semester. It's going to be great. But for now, it's not a bad thing that we're not hitting those things. In fact, it could be distracting at this stage. But there is nuance there that is interesting and fun to learn about. Other questions about that? Great question. Other questions about what we're seeing here so far? All right, cool. Oh, here, I can rerun this, I think. Yeah, now it's the better version. All right, testing. Okay, cool. So yeah, okay, although we could adapt our simple assert test from the original Sphere implementation, like look, at this stage, it's getting to be kind of annoying, right? Like, really, you know, there's nothing wrong with creating an instance of a class like this, right? I've created a sphere class, which needs a point 3D, so I'll just create the point 3D right then and there, just throw it, give it as an argument to the object, whatever. Personally, there are perfectly good reasons to do it this way. This is arguably a good reason to do it this way, but personally, I kind of don't like doing it like this. Let me show you what I would prefer to do is like, and then I would do like this. I prefer to do it that way personally. Now, why is it fine to do it the other way? Well, look, I don't actually need a reference variable called point A to reference this thing because all it does is immediately give it to that. It's kind of like redundant, for lack of a better term. Like there's arguments for not doing it this way and doing it the other way, but there would be a lot of cases where doing it this way is more beneficial or helpful, right? I'm a big believer in make your syntax as good as possible to explain what you're doing. But on that point, you know, like if I wanted to compare, like if I wanted to test the method distance between edges, okay? I need a sphere object. I need another sphere object. And I need a point 3D object for that sphere, and I need another point 3D object for that sphere. So I'd have a lot of like setup to do before I can actually test that method. You see? Where like before, sure, with our regular functions that we're writing, like think back to like Celsius to Fahrenheit, for example. Yeah, there's setup in a sense that like, well, there's different arguments you can give to the function and check its output. But here, because we have to create objects and some of them, oh, wow, look at that, cool. I've blocked so many ads, wow. I know, right? Thank you. So the point is, there's like more setup required now for all these assert tests. And it starts to get pretty hairy, right? Like, so, okay, all of our tests are now becoming increasingly complex and requiring more and more like setup. So now we need to make instances of point 3D and then our sphere objects before we can actually test anything. Okay, and like think about it too, like every time you want to test, like, well, what happens if the point 3D is at the origin? What if it's not? What if it's in the negative place? What if it's, that's a lot of different objects we're creating. That's a lot of bookkeeping to keep track of. It's becoming hard to like tell tests apart. Like, oh, I don't have an example here, but the tests are becoming like this like wall of assert tests. It's hard to tell them apart. It's hard to tell what am I actually testing here. Like we could say, like if I say sphere A dot distance between centers sphere B, I could say like, oh, it's testing the distance between centers. But let's say on the line before I say like sphere X dot distance between centers sphere Y. You're like, okay, well I'm testing the same method, but presumably the two spheres are actually different in a way. So like what's the significance between sphere A and sphere X and sphere B and sphere Z and or Y or whatever? Like there's a lot of information that's lost now. Okay, so it becomes harder and harder to know what on earth each test is testing. It's not easy to like look, right? Like here, right? Assert whatever absolute sphere dot distance between edges, blah, 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 minus that. And you're left going like, okay, maybe I can piece together what on earth that's doing, but it's not immediately clear. I have to like look at this and think, okay, I have to think about it. Like if I like, what is this testing? We could say, well, it's testing this method, but like under what conditions, right? It's hard to tell. Where if it was like Celsius to Fahrenheit and you put in like the argument of 32, you're like, okay, well, you know, that's the funny little edge case, right? Is your hand up or is you just stretching? Just chilling, okay. It's also hard to get a sense of how thorough the tests are, right? Like, sure, we tested the distance between spheres, but maybe we should test like other cases as well. If we want to be more thorough in the distance test, there's going to be a lot more duplicate. There's going to be a lot of duplicate code. Fortunately, though, Python and many other programming languages give us a nice tool for managing our tests in an effective way. And the tool we're going to use, because it's part of the standard library of Python, is called unit test. Now, I will warn you, unit test is ancient by Python standards. And as a result, it's got some funny little quirks to it. For example, it breaks like naming conventions, which is kind of amusing, but they never updated it because if they updated it, it would break everyone's code that used it before. It's a whole thing. There is arguably a better unit testing system called PyTest that we could be using for Python, but it's not part of the standard library, and it'd be a bit of a to-do. And there's nothing wrong with unit test. And also, unit test is more similar to what we'd be doing with Java anyways, so there's a good reason why I'm using unit test. Oh yeah. It was spooky. It was only me though?
No, yeah, we got.
Just now or earlier?
I got like 20 seconds ago.
You did? How come no one else was yelling?
I went to my earbud, that's why I didn't read it.
Well, I just heard 30 people talk. What? Did no one else's go buzz though?
Mine did it like 20 seconds ago, which is 20 seconds.
Oh, okay, but mine's on silent. Maybe it's not. It certainly is. Well, mine's on Do Not Disturb all the time. Gee. My phone really wanted me to know, I guess. Okay. Anyways, you have a question? About this alarm or? No, yeah.
Before the class of point3D, if you had defined a point and then ran the class and then tried to print the point A, would it return like the F string you have there in the repr, or would it?
Well, here, whoops. Like here. I'm not quite sure I understand your question, but let me show you this, and maybe this will answer it for you. Like if I get rid of the repr in the point 3, oh no, that's the sphere. Oops. If I go up here, and we comment out the repr, thereby like it doesn't exist. It's like we never wrote it. And I rerun this, and I go down here and I run this. We see, oh, well, I got to rerun this. There. Does this make sense, right? So like, oh, it's using the point3D's repr, which was the default one, which is kind of not helpful. Does that answer your question? Was that your question?
Yeah, I think so.
Like, are you sure? You don't seem convinced.
Yeah, I think so.
Okay, cool. Yeah. Other questions or anything? Now's a good time to ask. All right. Okay, cool. So, unit test is the next thing we're going to do. All right, so like I was just saying, our cert tests are becoming increasingly more of a pain to deal with. And that's to be expected. They're not going to scale well. They were great for the early stuff, but they just don't really scale very well. Also, another thing about the assert test that was kind of annoying that you almost certainly observed was, one, if a test failed, all it would do is crash. It wouldn't tell you like why, right? And if you wanted to know, like, well, you'd have to print out the result before it crashes. Remember, right? You're like, oh, they're not equal. Well, why not? What was it? It was supposed to be 7, but it just crashed. What was it? I got to print it out before, right? Okay, kind of a pain. Not a big deal, but kind of a pain. And also, like, if you had 20 tests and the first one failed, well, what about the other 19 tests, right? You got to get that first one working before any of the other tests run. You know, maybe knowing which other ones ran successfully and which other ones failed would help you debug that issue as well, you know? So the fact that it just crashes is not that helpful. But unit test, on the other hand, gives you a lot more information. Unit test provides us with a nice way for organizing and running our tests. And it gives us, like, whenever we run the test, it gives us a lot more information. It'll say things like, oh, this test failed. It was expecting 7 and got 17, right? Like, it'll tell you a lot more information. All right, so, yeah, okay. Fortunately, Python provides a nice tool, unit test. Unit test provides a lot of functionality, special assert methods, automated testing, shared setup shutdown methods, subtests, nicer test result reporting. There's a lot of reasons why we like it. We're only going to scratch the surface of what you can do with a testing environment like this. Now, I've also been saying it a lot, and I'm going to say it again. I haven't said it in a while, but your code is useless if you don't write tests for it, right? It means no one wants to see your code unless you also provide the unit tests for the code. Then they're willing to listen to you. Otherwise, you've just got this, like, I don't know, like I'm not going I mean this in the nicest way possible. No one believes you, okay? If you're like, I wrote code to do this, they're going to say, did you? And you could say, yeah, here. Now, unit tests, there's no way that the unit tests are going to like prove that it's correct, but it hopefully provides a lot of evidence that, okay, if they're well-written tests and they all pass, I'm a lot more comfortable with your code. Code is useless without the tests, okay, without the test showing that it's correct. And we've been doing the assert tests, but now we have a better, more systematic way to do it. So you always want to write your tests. And also, and we talked about this before, writing tests have more value than just like demonstrating that it's right. When you sit down and think about, okay, how I wrote my code, so how should it behave under this case, that case, the other case, that case, what about that case? As you're thinking about it, you might realize, oh, yeah, okay, what about that funny thing? It helps you write better code before you even run your tests. In fact, there's a whole style of development called test-driven development where you don't write any code until you wrote all of the tests beforehand. And you might say, well, how could I write the test for the code before I even know what the code is? Easy, because if you know how the code is supposed to behave, you could write the tests. If I told you, go write a bunch of tests for a function called Celsius to Fahrenheit that converts Celsius to Fahrenheit, you can do that without having the function Celsius to Fahrenheit. So you, by virtue of thinking about how it's going to work in all those possible cases, you can like define its operation very clearly before even writing any line of code. So we like our tests. Always write your tests. If you ever have a prof that makes a comment or never brings up tests, don't trust them. You shouldn't trust those profs, okay? And think back. Professor Hughes said, write my test. I should do the test. Listen to me, not them. So, unit tests. So, like I was saying, unit test is part of the standard library. I brought this up before, but I'll say it again just to make sure it's clear. The standard library is, look, when you download Python on your computer and you want to start writing code, there's a lot of code that Python wrote for you. There's a lot of functions, classes and whatnot that Python like pre-wrote for you. For example, the print function. You never had to write the print function, but I'm happy it exists. The list class exists. They defined what a list is. You've all used lists. You didn't have to define the list class before using it. It already existed. And there's a bunch of functions and objects and whatnot that you get for free when you load up Python, okay? Like print, absolute value, etc. But we also saw that sometimes we needed to import things, like the math, right? We needed to import math before we could do like SQRT, right? Yeah, we could cheese it by doing like to the power of a half, fine, whatever. But we could call SQRT or like sine and whatnot, right? We'd have to import it. Just because we imported it didn't mean it's not part of the standard library. It just means that the standard library is friggin' huge. And if you wanted to load all of that code into your computer's memory when you just want to write a program that like prints hello world, that's a waste. That's a waste of time and literally energy. So we don't do it. It loads up a minimal set. But rest assured, there's a lot of useful stuff that it includes, including unit tests. So although we're importing it, it's still part of the standard library. There are other things, and this is true for other languages as well. Anybody can go write like a package for Python, okay? And you can download that package and use it in your code. It's perfectly fine. That's normal. But they're not part of the standard library. That doesn't mean it's bad, but it just means that it's just not part of like default Python. And there's a lot of very popular packages and libraries out there that people use, like NumPy and Matplotlib and SciPy and sklearn and everything. There's a lot of existing things out there. It's not part of the standard library, but exceptionally useful. We don't need to download anything special to use unit test. PyTest is not the standard library. You would have to go download PyTest to be able to use it on your computer. And what's tricky about that is like if you wrote code that used PyTest and you gave it to him, his wouldn't work. And he'd have to know I need to go download PyTest. And there's ways to like let him know the right way and whatnot. But with unit test, if he's got Python, he's got unit test. So there's a reason we like the standard library. Okay, so here's how you start writing unit tests. I will also warn, pardon me for a moment, the way we would run our unit tests on Colab, it's kind of weird. It's not hard. It's you add this magic line of code that makes it run, but typically that's not how you would run it on your computer, but just FYI. So here's how we do it. We import unit test and we actually write all of our tests within their own class. Now, you will see something funny here. Because we've defined classes before. Class, whatever your class name is, right? But we always ended that line with a colon. Here, sure, we've got a colon, but we've got parentheses, almost like we're writing a function or a method. This, I'm not going to get too much into the weeds. I will tell you what it is, but don't worry too much about this. This is a topic for like next semester. This means we are effectively extending an existing class. We are calling our class TestSphere, where we're going to write everything we want in the TestSphere, but it's also going to include everything in the class test case from unit test. This is part of like inheritance. That's all I'll say about it now. Long story short, it's the magic code. Okay? I know. I hate magic code. It is what it is. Think about it this way, though. Imagine I introduced this to you. Yes?
So if we were using like point3d, we would just replace sphere with point3d.
You would say point3d test. That's literally what you would change. Sphere test. Circle test, yeah. Does it have to be called test? No, but yes. Not just by convention, but there's also like, it's funny. Just bang, nailed it. So, yeah, there we go. What else was I going to say about it? Yeah, I was complaining about the magic code, but trust me, this magic code would have been a hell of a lot worse if, imagine when I was starting to talk about a cert test back in like week 2. And I'm like, oh, write this code, class sphere test. You'd be like, what is a class? Yeah. All right, so here we go. What's going on? In the above example, we are going to import. Okay, great. Although it's not needed in Colab, depending on how we have our test set up, we may need to import the class being tested. That's also true, right? So if I wanted to test the sphere class, depending on how we're doing things, we don't need to do this in Colab, so don't worry about it. But depending on how we're doing things, if we're testing the sphere class, we might just need to say like import sphere. But don't worry. That's not an issue for us right now. As a convention, we call our test classes some class test, where some class is the name of the class that we want to test. Since the test that we're focused on, the class we want to test is the sphere class, we call it sphere. And just like you said, if we wanted to test the point3d, we would call it point3d test. You will also notice the unit test case within the parentheses next to the class name. Like I said, the nuance of this is outside the scope of the course, but in short, we need this in order to make the unit test framework work. Okay, that's it. So here's how we would go and start writing our unit tests. Now, the name of these tests, depending on how we have our environment set up, the way we have it set up with Colab and whatnot, our tests must start, our tests must start with test underscore, okay? Now, this is not actually true in practice because you can tinker with settings to make it such that this is not the case. For our needs, every single test that we write will be a method within the sphere class. And the name of that method always starts with test underscore, all right? Other than that, the names of these tests, so with the exception of the fact that it starts with test underscore, the name of the test doesn't really matter, but we are going to follow a convention, a very important convention. The convention is always going to be the what, the conditions, and the expected result. More on this in a moment. But here's an example of 2 unit tests. Def test sphere center point returns correct point3d. What do you think that test tests? Well, I think it tests if we get the center point from the sphere object, if we get back the correct point 3D object. How did I know that? Because that's what it was called. Usually when you're writing like methods and functions, you want the names of your methods and functions to be as like clear but succinct as possible, right? Like Celsius to Fahrenheit, right? You don't call it take a value and convert it from Celsius to Fahrenheit. Like you don't call it that. Like you want to give it a good name, but it's like succinct, like to the point. With our tests, you want them to be as absolutely clear as possible. It's not verbose for the sake of being verbose, but if we follow a naming pattern that's very, very, very clear, there's no ambiguity. Because when you hit run on all your tests, and you've got dozens of tests running, and you see a line that says, test sphere center point returns correct point 3D, failed, I know exactly what went wrong. I'm not left going like, oh, what's that poorly named function actually doing, or method actually doing, right? So we've got a nice, good, clear name. And how is it going to work? Well, we're going to create a sphere object with a point 3D 321. Why is it 321? It doesn't matter. All that matters is that we've got a point 3D. Then we call self.assert equal. So this is a method. It's within a class. It starts with self. And interestingly enough, this is calling the method assert equal. That exists within the class sphere test. Now, you might look at this and say, where's the method assert equal? You never wrote it. I see two methods there, none of which are called assert equal. That comes from here. Okay, we inherited it. That's some of the code we get by throwing that in there. So if you were wondering where it came from. And remember how I said a few moments ago about how this is an old package that existed in the time before conventions were set with Python? You might look at this and be like, wait, you said write all of your methods with snake case. But this is camel case, right? Like I say, write your methods with underscores, right? But here it's assert equal, right? You see? This is called camel case, and this is not the convention in Python. If you do this in Python, everyone gets mad at you, unless you're talking about like a class name. So what gives? It's so old that this was written in a time before the rules were kind of like set in concrete. So that's why, if you ever wonder what's going on. Anyways, we call a special method called assert equal. What do you think that method does? It asserts that two values are equal. And what are we going to do? Well, we say, well, okay, the point 3D, 321, better be equal to getting the center point from the sphere I just created. You see? Now this obviously would require that the point 3D class exists and has an equals method, because otherwise it wouldn't know how to compare point 3Ds. But there you go. Here, perhaps this is a simpler one. Test sphere radius returns correct radius. What's that going to test? Well, I'm guessing if I have a sphere and I say, hey, what's your radius? It better give me back the right number. So create a sphere with some arbitrary values, but the point is I put an 11 here. So I better get back 11 if I ever ask the sphere what that radius is. Do you see? Yes, no, happy, sad? 2 thumbs up. All right. So there we go. Cool. Questions, thoughts, concerns? Yes? I absolutely will. Let me go down here. Here, yeah. Okay, so I ran it, right? Now, when I run this, all it does is define the class. I need to tell Python, okay, run the tests. And if you remember, a moment ago I was saying there's some like annoying magic code we have to write. You'll notice I'm also scrolling for it because I honestly don't remember what it is. Every time I run it, I need to, oh, come on, it's got to be in here somewhere. Running, yeah, here. There. Boom, there we go. So here, I ran that code. okay? And I can see, oh, test sphere, I ran them. Look, wow, that was fast in 6 milliseconds. Cool. And yeah, everything was okay. Nothing failed. Looks good. The results are okay. Awesome, right? Now you were saying, well, what happens if it's wrong? So let's say, for example, okay, I'm gonna break this test. Now this is not broken because the class is broken. This is broken because like my unit test is wrong, but it'll still show like the test is failing. And now we see failed. Test sphere radius returns correct radius. I know where the problem is. It's something to do with my radius. And it failed. Why? Well, you will see that 12 is in fact not equal to 11. That's why it failed, which is nice. But we also see that both tests ran. Now you might say that's because that was the second test that was being run. So just to put that to bed, we can do this. There. Still fails, right? Like it fails. But both tests still ran. One passed, one failed. Pretty neat. Yeah, cool. And okay, you know what? For the sake of demonstration, let's fix that one. And let's just go back to here. I'm going to change this to be like, I don't know. Clearly this is nonsense, right? Like it gives it a radius and it's going to assign the radius the wrong value, meaning that if I ever get the radius back, it's going to give me back the wrong answer. So now I'm breaking the actual class, not just the test, or not the test. And we will see, well, it's failing. 11 is not 22. So yeah, it fails. I know, right? What's going on? All right, cool. Cool. Now this is just 2 tests. And don't get me wrong, there's a lot more power to what we're doing here. So writing the unit tests. Okay, so above are 2 tests confirming the correctness of the constructor and the attributes coming back. By the way, just in general, I included these tests for like demonstration purposes. Typically, it wouldn't be crazy not to see tests for these because people would be like, I'm going to assume Python is going to work the way Python does. Meaning like, look, if I assign the attribute to 11, it's like, imagine saying like, okay, I'm going to assign the value 7 to a variable. Let's write a test to make sure 7 comes back from that variable. Okay, look, I think Python, like we can assume that that's going to work just fine. So someone might make an argument that these are entirely unnecessary. Okay, fine, but they're here. It's not, maybe not bad to have. All right, so key things to note here. The tests are methods that belong to the class. Each method parameter list is just self. This could change, but it must at least begin with self. And each method starts with test underscore. The method names are descriptive, so it's easy to know what it's testing, and the test prefix is required, but I did say you could actually change this, but don't. But what's after the test underscore doesn't really matter. We make use of assert equal, which is the method. Although we did not write this method, we got it for free from the inheritance thing, that like unit test.test case. And we use assert equal here, but there are a lot of other assert things. Like there's like assert equal, assert almost equal. There's like assert true, assert greater than, assert less, whatever you want, there's a lot of them. And the method provides a simple mechanism for setup code to be grouped with the test itself. So now you'll also see that like, yeah, like if I look at this code without that setup code, right, I would go, well, I mean, I guess it expects it to get it back, right? Like, I guess so. But because it's grouped with it, it's like, well, it sure better be, right? Because it's more obvious. It's right there. It eliminates the guessing, which is really nice. Each test should test one thing. This is a common mistake. People are like, well, I can write a test that verifies like 5 things. No, don't do it. Each test should test one little thing. There's a lot of reasons for it, but perhaps the simplest, most obvious is if your test fails, if my test that does all these things fails, well, why did it fail? Which of the 7 things did it not do right? Anyways, we'll pick up here on Friday. For those of you that have lab tomorrow, well, we're back to throwing you into it, figuring out unit tests before we finish talking about it, but you'll be fine. Because that's what the lab is about, unit tests. Last chance for questions? All right, I'll catch you all later.